Right. So I'm the chief scientist at a small British company called Push Technology. We essentially do messaging systems. But we do it differently. We do it for more machine to human. It's about experiences with server-side systems on a mobile or the web. So we break all of the rules. And I'm going to talk about conversational big data. Okay? So what is big data? At the panel discussion earlier, we retermed it quant data because you had us at value. People talk about size, volumetric. It's not about that. It's about extracting value from data. Some interesting article on LinkedIn this week talks about it's about the connections, right? So it's so much about the conversations, it's about the value, it's about the connections. So we're already at a point where we've got, say, with 1 million devices, if 0.001% of them are connected, you're talking about 5 million connections. And the more devices we have, as we have device expansion, well, we got a lot more connections for those devices. So things are getting massively interconnected. And it's those interconnections that creates this opportunity to innovate with messaging in the way that NoSQL has emerged to have specialized databases that do specialized things with data. So Cassandra is time series oriented. It's no longer relational data. So the same thing really needs to happen with messaging. Okay? So I'm talking about the communication aspects of big data, getting at the value, accessing those result sets. So Intel, earlier in the year, came out with this really interesting infographic on what happens in an internet minute. Okay, so we can see there's 6 million Facebook views. There's about 277,000 logins in a minute. There's 1,300 new mobile users every minute. 204 million emails are sent every minute. So again, massively interconnected. We've got a lot of data being distributed over this network today. And if we zoom in, so my background is kind of capital markets, so I'm small data that's really fast. Most people are kind of used to web scale, so draw something, for example, is about the same order. So cap markets, so in currencies, you might send the data 10 times more, 10 times faster, but this draw something data is 10 times bigger, so it kind of balances out. It's a good proxy, okay? Make sense? Good. But the last mile is actually really, really hard. Okay, this is my home broadband. This is in kind of 2007, right? You see this red line? That's what I'm actually receiving. I measure the latency and the throughput. That's what I'm purchasing. That's what my ISP actually sold me, right? So I actually left and went to another ISP, and I got the same red line again. Okay, so that's home broadband, and mobile is a lot worse. You get up in the morning. If you get up early, you get about 2.5 megabits on 3G in London. At 9 o'clock, when everyone's commuting and checking their email, you get about 0.5 megabits per second. Right? So latency isn't fair either. Right? And then the last thing that we're going to look at is machine to human. So this is conversing with people, interactive data. Right? This is about humans. It's not about systems and data. So messaging has come from before the internet. Okay? So it's ancient. No one has reconsidered the first principles. And we're going to do that. That's basically how I'm going to approach the talk today. Okay? So traditional messaging, you've got producers and consumers. It's loosely coupled. These are all good things. You've got queues on each side. It's very good for durable subscriptions, for example. But again, it was invented when that was in your pocket. Well, hanging off your hip, really. It didn't fit in your pocket in those days. Anyone remember these? Or DEC message queues? This is before AMQP and Rabbit and Zero and all the cool technologies we know today in messaging. And they were very hard to actually configure and deploy and operate. I used to support this in a manufacturing environment. It was a lot of pain. So we don't like pain anymore. We're trying to move away from that. And the fallacies were simple. So inside the network, it's reasonably reliable, right? It doesn't fail so often as you might think. And the latency, it's typically fast enough for most of the things that we're interested in. But it's not the same over mobile. You're going over long distances. It's highly variable. It's using radio frequencies which get interfered, and there's a lot of retransmissions, a lot of retries. So it's not the same. Okay? So in 1992, 20 years ago, surfing the internet was coined as a term. The internet happened. Web browsing, Mosaic. The first SMS was sent. This is 20 years ago. We haven't redesigned messaging really in that time. And I think it's now starting to become obvious that old school behind the firewall messaging over the internet just really doesn't work. Okay, so that's exactly what I'm going to be talking about. This internet thing was really popular, so it grew and it grew. And then in 2007, the God phone was invented, right? We started to be able to get internet on our phones while we're moving around and we're walking, on our tablets, on our iPads, our Nexuses, whichever one of these devices we happen to be using today. So now you've got the internet and you're portable and you're moving, okay? So we started touching the internet, right, on our phones and on our tablets. So we put everything into the internet. This is cloud, right? So all of our software and platforms became services, and they became hosted in a utility somewhere. And you can turn on power just like a tap. You can turn on these services. You can outsource skills and people. So you can, all the specialties, rather than you running your own production platform or having your own data center, you just use the awesome people at Amazon or Rackspace and let them solve that problem. You run whatever it is for your business. It's now cheaper for you to innovate and do what it is that you do. All right? And it grew like all the good things do. So we invented big data, right? Because now we need to pay for building all these clouds, right? So we invented big data to work around that. It's a marketing term. We're going to have a technology talk. It'll get more technical as we go through. Okay? It's nothing new. There's a big problem, though, with most human experiences on the web. Hands up who likes Twitter, abuses it a lot, rants on it? Everyone. Okay. You know when you post something onto Twitter and it goes, whoa, something wrong happened. And you go, so you send your tweet again, and then it says, I already have that. Right? Why are you telling me? So you got it, don't tell me. Just at some point later, you can be eventually consistent. It doesn't. It's immediately inconsistent. Whoa, something bad happened. So you resend it and it goes, oh no, I've already got that. Right? That's confused you twice over something that it should have just done right the first time. And even if it did fail, it certainly shouldn't expose it to you. Right? We're expecting higher grade experiences these days. But it was really successful, and it grew and it grew. Okay? So hopefully now you're realizing that latency isn't perfect and bandwidth isn't free, and there's lots of issues that are more nuanced today than they were before. Okay, so this is about nuance and trade-off, and that's why we have this specialization in the storage community. Okay, the same really needs to happen for messaging over the web, especially when you're interacting with things in real time. Okay? So why do we want to do this? Is the core of what big data is about, right? It's what value do we get out of it? What insights do we glean? What implications are there for taking or not taking a certain decision? What and how is the technology bit, but we do it because the why is where the money is. Okay? And the way I do it, essentially, is to measure the nuances and trade-offs, and I'm definitely trading for this human experience and trading away certain things. I can't have everything. I have to take something, I need to give something away. Okay? There has to be balance, and these are all benchmarks, so we're going to go deep into some numbers in a second. All right? So conversational data, or conversational big data, interacting with these streams of content that we're generating at higher and higher frequencies for more and more heavily connected devices, will require a lot more intelligence around communication, sending the right data at the right time. So it has to be relevant, timely. We want it to be a responsive set of interactions. We don't want these, whoa, you've already done that moments that we're getting with existing platforms and systems. And we have to understand the device and the context within which those mobile endpoints are communicating with us. Right? At 9 in the morning in London, on my phone's ISP, I only get 0.5 megabits per second. During the day, around lunchtime, it's about the same. Most of the rest of the day, about 2.5 megabits. Right? If I'm traveling to, say, Berkshire and back in the train, it's variable connectivity all the way. Right? If you go under a bridge, you lose your phone connection. It's gone. What happens when you get out the other side of the bridge? You've got to recover all of that data if you're interacting with something. What happens with that state that changes on the server side and on the client side while you were under the bridge? So we're trying to solve those kinds of problems so you don't notice that gap, that delay. It recovers seamlessly and elegantly. So we changed messaging. Okay? So you know the queues on the client side in a typical messaging system? What happens if I move them to the server side? Well, now when your bandwidth drops, and this queue backs up. I can see it backing up. I can drop the rate of messaging I'm sending just for your device, or just for your device. You might suddenly find a Wi-Fi network. Suddenly you've got an infinite amount of bandwidth compared to you, for example. So we can actually adapt and tailor the services in real time. It becomes smart or adaptive. Now that's one change we can make. We can store state inside the messaging system. We don't just have to treat it as stateless and pass it through. We can store and cache it. Now it's one hop closer to your device, which could be useful. Okay, so we're now we've got this traditional topic space for messaging. It's now fundamentally distributed. It goes across the network. Okay? Another thing we can do is exploit the physical data structures. Right? So now that we have the data in memory, we can actually have a look at it and go, is this different to what I sent before? If it isn't, don't send it again. Don't repeat yourself. Don't resend the message because bandwidth and latency are expensive. Okay? So we can start to do things like that. So the messaging kind of I work with, when you connect or subscribe to a thing, it sends you a snapshot of what it already has. And subsequently, it sends you deltas of change or updates because you're not interested in most of the repetitive, redundant information anyway, so we don't send it. Okay? Think about it. If you've got low capacity, low fidelity devices, this can make massive savings. Okay? Another thing we can do is we can inject logic inside the engine. So if you don't like the way we built it, you can kind of roll your own. You can entirely change the way the messaging product works, which is kind of cool. So if you wanted React-style routing, then you could just plug in a Dynamo thing that does it that way on a ring, for example. And you could represent that in the topic space in a Dynamo-like way, if that made sense. Okay? And the last thing we can do is something called structural conflation. Okay, so this is an instance of complex event processing inside a messaging system. So most people are used to business intelligence, workflow tools, iterates and futures now. They're used to these as things in and of themselves. But if you use that as a framework and a plugin inside a messaging engine, this is what it ends up looking like. And we're going to go slightly deep into this. Okay, so in a normal messaging system, you've got a queue of events that you're pushing in. So that's the left-hand side here, from my left to your right. And on the right-hand side, on the other side of this queue, you're going to receive on the other side of the system. In the system I work, this client-side queue is on the server side. So we haven't sent the message yet. We haven't incurred the cost. So if I'm using replace conflation, if I have two topics here, so there's two values about to be sent, and I go, why don't I just replace the newest value in the slot of the one that was earliest out on the wire? Okay, so you get 3 messages rather than 5. It saves bandwidth and it's always current, right? Because current information is important. We want to avoid buffer bloat. Okay? I want to reduce the amount of data that I'm sending to absolutely the most current and reduce the volumetric of that down as well, actively. With merge conflation, we're doing the same when we're performing some computation or operation on that data at the time that we're conflating that down. Okay, because there's only 3 good sizes of queues. 0, I have nothing in the queue, I have nothing to tell you. 1, I have something to tell you. And greater than that, I'm boring you. We should stop doing that, especially over high latency mediums such as the internet and the web. Okay, does that make sense? That sounds really good, but does it work? So let's measure it. The second part of my talk. Performance isn't a number. Okay, it doesn't go to 11, right? Most benchmarks and white papers that you might read, people will go, we measured this at 1,000 bytes. And you're thinking, it must suck at 1,001 bytes and at 999 bytes, right? Why do all messaging vendors do this? They give you, here's our results, we're using the C10K thing, and we're doing 1,024 bytes, exactly. You're going, something's wrong here. You either can't do really big messages or you can't do small messages. Okay, so we should pick a spectrum. And they idealize the benchmarks to make their product look really good. Here's how I approach it, or how my company approaches it. So we take throughput and we find what's the worst possible thing I can do to a machine. Well, I'll just saturate it, right? So at a regular rate, I will throw 750 new concurrent connections at the server, right, every 5 seconds. Here's another 750 connecting at the same time. Just throw it at the server and see what happens. And we do it across a range of message sizes. For a soft designed rate for these clients, they should be receiving about 100 messages per second. So it's a fairly good throughput test. See what breaks when, right? It's a stress test. Something has to break or we're doing it wrong. That's fair, right? It's fairer than here's 1,000 bytes. Oh, look, all the other message sizes are wrong. Use 1,000 byte messages. That doesn't work like that. For latency, I'm going to show you the best case. It doesn't get better than this, right? So I'm going to run a single client with a single message. I'm going to ping pong. Divide it by 2, you've got the single hop, right? Performance in real systems, you're not going to run to breaking point to saturation. It probably won't be as good as this because you'll have more than one client. It's going to be somewhere in the middle, right? You've got a ballpark where you can go, that's where real systems live. Does that make sense? So here's what regular messaging looks like. Okay, so we can see larger message sizes here are red. Quickly ramped the machine. I tested this onto saturation. Okay, these are running 10 gig NICs. So you can see after about 30, 40 seconds, that 10 gig NIC is saturated. Right? There's 1.25 gigabytes or just under going between two machines. See, for smaller message sizes, it doesn't saturate at all. But smaller message sizes are much more expensive to marshal because there are more of them. So you saturate CPU for the smaller message sizes. Okay, so and this is a 5-minute run. Does that make sense? It's not conflated. We're just sending as many as we can. We're continuously ramping clients. Once it saturates, interesting things happen. So here's what happens when messaging breaks for a regular messaging system. And the really interesting thing, if you've already noticed, you see this waveform? That's back pressure, right? So you get back pressure from the cards. They're running as fast as possible. You're still throwing in new clients every 5 seconds. Here, take another 750 clients. Something's going to break. So new connections, they just get refused. Connections that are now being badly served get dropped. Things break. It's supposed to break. It's stressful, right? And different cards actually give you different, kind of the same amplitude but different wavelengths. It's really interesting. If you pick a low latency card, you get a different amplitude than if you pick a regular commodity off-the-shelf 10 gig card. It's really interesting. But something has to give. Okay? Does that make sense? So for smaller message sizes, these kind of blue ones, 125 bytes, we're doing about 5 million a second. For the larger ones, 2,000, about 500,000, something like that. It's kind of the range. Okay. If we use conflation, however, you'll see it takes slightly longer to reach saturation. And for the smaller message sizes, it starts to taper off quite quickly. Because you see those queues? We're dropping messages. We're only ever sending you current messages. So the higher frequency of messages in for a really fast producer, you get more value. We never spam the client, right? Make sense? It's always current, and under merge conflation can be always consistent too, because you can perform computations on these queues. Right? Remember, they're on the server side, so you haven't sent anything yet. Okay? Okay. Is another view of this data is this from the client perspective. Notice how the waveform is gone. It just adapts. Right? Saturates down so you can handle more concurrent connections. Right? You can send an increasing number of messages, but the QoS will adapt accordingly. Okay? So it's more stable beyond the point you should ever run this in production, I might add, but it's still more stable. You can measure the effect of conflation. Okay? You can see it. Right? It's fairly obvious at 2,000 bytes, reasonably obvious at 1,000 bytes. And for the smaller message sizes, you don't see it so much. You start actually hitting CPU. It's really interesting. 2,000 bytes, you just saturate those 10 gigs. 125 bytes and less, you're going to saturate those CPU cores. It's really interesting. Okay. The kind of numbers we're looking at is about 1.09 gigabytes of payload data, not WebSocket framing, it's not TCP or IP overhead. It's pure business critical data out to all of these connected clients. Okay? That's about 87.2% efficient. It's pretty efficient. Okay? So it's all business value data that's going over the wire. And the latency is pretty good. Good latency spikes are on the left-hand side, and they're typically spiky. Okay? You see there's some variation across the message sizes, but it's nice and tight. It's actually the marketing version. There's a lower latency log version that's got a little hill here, but it's 3 orders of magnitude less than that nice set of peaks over there, so we can ignore that. Okay. So, let me just skip these two and go straight to this one. So, the server I work with is in Java, right? And state of the art in Java today, people are hitting around 5 microseconds in terms of messaging between two boxes. State of the art in C, or assembly, you'll be hitting about 2.4 microseconds. You're hitting the limits of the actual hardware you're using to get a message from A to B across the box. And then crazy people use FPGAs and don't bother with boxes and operating systems and stuff like that, but it's really expensive. Okay, so this is quite a good place to be in for something that's going over the web to mobile. But I hope you've gotten the point that it's not about really latency or ultra low latency. It's about, if you minify the cost of everything, then what you have left is overhead to soak up more load or to provide more capacity with less tin. This is about cost. This is about saving money. That's what big data is about. It's about value. It's about providing a service cheaper, right? It's getting better skills for less up front. Okay, that's the meaning of big data. And we're trying to do this over the web and make it conversational. Okay? So, kind of a theme throughout this conference really has been, it's about the data, stupid, right? That's basically what this conference is all about. It's not about Scala or Akka or Haskell or Erlang or Java or anything like this. It's about data. Right? We send data because it's valuable, so maximizing for value by sending important data makes sense. But once we have the data, what do we want to do with it? Use the Play framework to visualize it. Or you want to process or analyze it in some way. So kind of you're getting into joins and merges and combinators and event processing. So the last section of my talk is really about stream processing. It's about complex event processing. Okay? But embedded inside something like inside the Play framework with iterates and futures, which was the last talk on this track. Okay, so this is CEP simplified without the complex. So I wrote a little framework called EEP because CEP is scary. So I gave it a scary name. But it's just CEP simplified and embeddable. Okay? So we have maps. So you can get a message, process it, add or remove fields, tuples, lists, elements, segments, chunks, and then return the result. You can take a subset of data that's streaming over time that's in flight. In CEP, these are called windows. Right, you can branch or split things. You can join, gather, combine, merge, temporarily pattern match multiple streams, produce a single output stream. And you can have in-memory state if you want. Right, very simple. They're the things that you do with messages. Okay? So I decided what was the most useful thing I can add, right? Well, it's Windows, right? Because a lot of the other stuff you might use for very specific things, but the most useful thing I use all the time, since leaving the CEP world, I still think in terms of these windows. They're very powerful. So a tumbling window, if I have n events, I'll gather these n events or accumulate these events. And when I've got those n events, I'll perform some computation. Give me the standard deviation, the kurtosis, give me the average, do some thresholding algorithm so I can make decisions in real time. And these are non-overlapping. So discrete n events followed by a set of discrete n events. It could be client or server side, it doesn't matter. It looks a little bit like this. If you were to wrap kind of a behavior and interface around this that has, you initialize the window, you accumulate events inside the window, and at certain points in time, depending on the window type, you'll emit results from the window. It's similar to your iterate with a result, for example. Of course, if you write this in, this happens to be Node.js, so it's JavaScript. If you write this in real code, right, in a real language, all these control structures you don't get any reuse out of. Right? You have to keep on rewriting these control structures, and although it looks innocuous, you'll get off by one. It'll go bad. So we want to write that once. So we can abstract that away by taking the function, the operation we want to perform, average, median, standard deviation, write that once and write it well. Right? So we provide that as a library. Okay? Now we can take this control structure and we can write that out too. So this becomes a window type. If that makes sense. So it should look more like this. This is much simpler code, and it's obvious what it's doing once you know what a tumbling window is. Does that make sense? Cool. It's quite simple. Now, sliding windows are much more useful, but they exhibit some unfortunate performance characteristics. So in a sliding window, let's say I have two events. A heartbeat from a server somewhere. I'm alive, I'm alive. The absence of an event, probably dead. So if you look at this and the absence of an event as a set of events, you'll be able to look at the current and prior. So if it was dead and it's now alive, well then it's alive again, so I should do something. I should fail back maybe to this system or something. If it was alive and it's now dead, it's gone down. I should fail over to something. Okay, so you can detect these events with a sliding window because it is overlapping. But if it's overlapping and you're looking back across a set of events in the past, although the events are streaming, so you amortize the effects of the events happening right now, because you're looking back into a window in the past, if that's a very high frequency, it's n times n. It's n squared, it's exponentially degrading for a larger n. Okay, most CEP engines actually implement sliding windows like this. It doesn't look much different from the tumbling case, once you know what a window is. Also periodic windows, so every 10 seconds, right, emit a set of results for a set of accumulations, and monotonic windows, right, because time can change, daylight savings, stuff like that, leap seconds, horrible things like that. So we have monotonic windows as well, which you have this little tick method, which updates an internal clock and then will cause an emission of a set of events. Okay, so monotonic looks pretty much the same. Okay, skip. So I call this EAP. It's on GitHub. I'm probably going to write it in Erlang. You're going to write it in Vertex. So it's kind of growing. If you're interested in event processing techniques, it's a good reference for a minimal, simple, lightweight implementation of CEP techniques. These are sliding windows. Notice it is exponentially degrading. And the performance is fast enough that you saw I was saturating these 10 gigs about 5 million messages per second. If your programming language can do more than this, stop. You don't need to go faster than that. So it doesn't matter how fast your programming language is. People go, oh no, you shouldn't use this language, it's slow. I'm going, yeah, but your network card is slower. So it doesn't matter. It doesn't matter how slow your language is, trust me. Latency over the interwebs is slower, it's irrelevant. What's relevant is send current information everywhere to all of the things. And please make that consistent, because humans don't like the, whoa, something went wrong message. That's just bad. It's bad design. We should stop doing that. Okay? And these techniques help you actually build this as a technologist, so they're really useful. Okay? But we can actually fix it. Anyone here got a mathematical background? Physics? Second law of thermodynamics?
Yes.
Okay. If things haven't gotten weird before, it's going to get weird now. Okay. So, see this algorithm? I'm back propagating the current value to the last set of events in the sliding window. This do-while loop is soaking up all of that performance. If I can get rid of it inside the heart of this construct, this algorithm, then it could go pretty fast. Agreed? It turns out you can actually do that. If you don't, your performance looks like this in a sliding window. You're taking a swan dive away from happiness. It's just exponentially degrading. It's bad. Right? The fix, and I'm pretty sure no one has done this in commercial offerings, is to use the second law of thermodynamics. As I'm sliding up through the window, instead, I have this compensate function, which reverses the effect of the value I'm about to eject from the window. Right? I have n events, so first 4 events arrive, and on the 5th event, I'll take the value of the first event that arrived, because I've got a window of size 4, I'll reverse it, so if I was adding, I'll remove. If I'm counting up, I'll count down. Or if I'm incrementing, I'll decrement. Got it? And I'll essentially rub out its effect. So as the window slides over time, right, compensate. Now the performance with compensation, which is a slightly different flavor of this window, see here? This 1 would have cascaded down, but I took the effect of that mathematical operation away. So if I use reversible mathematics, I go from n squared to linear performance, which is interesting because one of the reasons why I don't use a lot of complex combinators and pattern matching in CEP was because these joins are really expensive. These joins are cheap, really cheap. But you need to use reversible computing. So all of the hard math you had to do for statistics, you now have to do it backwards. So it's reversible. But some of the benefits are you can now slide backwards through time. You don't have to go forwards. So it solves that problem too. I don't know why you'd want to go backwards in time, but you could totally do that with reversible aggregate functions. Make sense? Cool. So conversational big data. So it's not really about big, it's about value. And when we're talking about conversations, it's to humans, it's to us, right? It's to peoples, to organizations, it's about social, it's about experience and expectation, right? So this all drives back to things should be relevant, timely, responsive, and we have to have sympathy for the devices and the context within which we're connecting and communicating to things. So that was my mad, mystical mystery tour through messaging. Why it should be revisited for the internet, the web, and mobile today, backed up with a few numbers and a little bit of event processing. Any questions? Still in shock? Okay.
I had one question. So you were talking about sending the latest data,
Yeah.
the most recent. Are there scenarios where you really want to keep the whole history and that's not going to be the right thing you've dealt with?
There are use cases that I work with where data is being sent into an organization. So for forensic storage, for example, so you're recording AV and text on a mobile phone, pumping it into corporate for forensic storage, where you want absolutely everything. In most cases, you typically want to drop down. What do we think of high-frequency data? It's like gambling, gaming, trading, prices. All this data is recoverable, right? So it's okay to conflate using replace or merge conflation or under some operation. And it's okay to tune the consistency to and not have it fully consistent under certain conditions for certain use cases. But there's certain things you should never conflate. Like, don't conflate a transaction like an order, deposits and withdrawals from a bank. Never conflate those things. This way madness lies. That's just wrong. So I think there are cases for both, and it's about using the right thing in the right way, more so than anything else. Most people are obsessed, you must use this technology, it is the best. And we go, it's the best for that thing in that way. Right? It's about the use case. There is no one-size-fits-all solution. Anyone who tells you there is selling something, so we're technologists, we should run away. Or point them at our non-technology people. Talk to them, they're awesome. They love buying things. Good question. Any other questions?
The Erlang version you're planning, is that based on something that's already there?
Yeah, it's basically similar to the JavaScript Node version, but it's more Erlang-y, and it's implemented in Erlang. So I've got that about half done, so it'll be on GitHub in about a couple of weeks. But it's the same kind of notion. So, for example, if you want to use a monitoring solution, use Folsom because it's awesome. If you just want to do these CEP-like things, it'll just have windows. It's very small. It does one thing and one thing well at the moment. It might add combinators later. So that will be on GitHub in about a couple of weeks. So I'm currently obsessing over should I leave it the way it is or rewrite it in C and expose it as an if for speed. So I don't know whether to do that yet. So, okay. Other questions? No. Thank you.